Hello there, and welcome to the Sleepy Knowledge Channel. Tonight, we'll be drifting into the mysterious, glowing world of volcanoes, ancient mountains of fire that shape our planet in silence and in fury. Beneath the surface of the earth, rivers of molten rock slowly move and breathe, waiting for the perfect moment to rise. Some volcanoes sleep for centuries, while others whisper with quiet plumes of steam, reminding us that the earth is very much alive. Every eruption tells a story of creation, destruction, and rebirth. The black volcanic sands, the steaming vents, and the shimmering lava flows are not just forces of chaos, but of renewal. From their ashes, new lands are born, and life begins again. As we wander through this quiet, fiery world, take a deep breath and imagine the slow pulse of the earth beneath you. Feel its warmth, its patience, its endless cycle. If you enjoy these calm explorations into nature and science, I invite you to like, subscribe, or share a gentle thought in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and let the peaceful power of volcanoes carry you. Let's begin. When you think about the most powerful forces on our planet, volcanoes surely rank near the top of that list. These magnificent mountains of fire have shaped our world in ways that most people never imagine. The very ground beneath your feet, the air you breathe, and even the water in our oceans owe their existence, in part, to volcanic activity that has been going on for billions of years. Volcanoes are not just destructive forces of nature that we should fear, but rather they are incredible geological features that have created much of the landscape we see today and continue to play a vital role in how our planet functions. The story of volcanoes begins deep within the earth, far below the surface where we live our daily lives. Our planet is structured like a giant onion, with different layers stacked on top of each other. The outermost layer, called the crust, is relatively thin and brittle, much like the shell of an egg. Below this crust lies the mantle, a thick layer of hot rock that behaves in surprising ways. Even deeper still is the outer core made of liquid metal, and at the very center sits the inner core, a solid ball of iron and nickel that is incredibly hot. The temperatures down there are absolutely mind-boggling, reaching several thousand degrees, hotter than the surface of the sun in some places. Now, you might wonder how these layers create volcanoes. The mantle, despite being solid rock, actually moves very slowly over millions of years because of the intense heat and pressure. This movement is similar to how honey flows when you pour it, except it happens so gradually that you would never notice it in a human lifetime. The heat from the core causes the rock in the mantle to rise toward the surface, and as it rises, it cools and sinks back down, creating a constant cycle of movement called convection currents. These currents are incredibly powerful, and they are the driving force behind many of the geological processes that shape our planet, including the formation of volcanoes. The Earth's crust is not one continuous piece, but is instead broken into enormous sections called tectonic plates. These plates float on top of the slowly moving mantle like giant puzzle pieces covering the surface of our planet. There are major plates and minor plates, and they are constantly moving, though so slowly that you cannot feel it happening. Some plates move apart from each other, some crash into each other, and some slide past one another. Where these plates meet, interesting and often violent geological events occur. And this is where most of the world's volcanoes are found. The movement of these plates might seem insignificant, often just a few centimeters per year. But over millions of years, this movement has created mountain ranges, ocean basins, and of course, volcanoes. When two tectonic plates collide, several things can happen depending on what type of plates they are. If an oceanic plate, which is denser and heavier, meets a continental plate, which is lighter, the oceanic plate will be forced underneath the continental plate in a process called subduction. As the oceanic plate descends into the hot mantle below, it begins to melt because of the incredible temperatures and pressures it encounters. This melting rock, now called magma, is lighter than the surrounding rock, so it begins to rise back toward the surface. As it rises, it can accumulate in chambers beneath the Earth's surface, building up pressure over time. Eventually, this pressure becomes so great that the magma forces its way through cracks and weaknesses in the crust, erupting at the surface as a volcano. The word volcano itself has an interesting origin that connects us to ancient mythology. It comes from Vulcan, the Roman god of fire and metalworking. The Romans believed that Vulcan had his forge beneath Mount Etna in Sicily, and the smoke and lava that came from the mountain were the results of his work creating weapons and armor for the gods. While we now know the scientific reasons behind volcanic eruptions, there is still something almost mythical about these powerful mountains that can change the landscape in moments and influence the climate of the entire world. Volcanoes come in many different shapes and sizes, and understanding these differences helps us predict how they might behave. The most iconic type is the stratovolcano, also called a composite volcano. These are the classic cone-shaped mountains that most people picture when they think of volcanoes. They are built up over many eruptions, with layers of hardened lava, ash, and rock stacking on top of each other like the layers of a cake. Famous examples include Mount Fuji in Japan, Mount Rainier in Washington State, and Mount Vesuvius in Italy. These volcanoes are often the most dangerous because they can produce explosive eruptions with devastating pyroclastic flows, which are fast-moving currents of hot gas and volcanic matter that can travel at speeds over 100 miles per hour. Another type of volcano is the shield volcano, which looks very different from the steep-sided stratovolcanoes. Shield volcanoes are broad and gently sloping, resembling a warrior's shield lying on the ground. They form when lava flows easily and spreads out over large areas before cooling and hardening. The Hawaiian Islands are actually the tops of massive shield volcanoes that rise from the ocean floor. Mauna Loa in Hawaii is the largest active volcano on Earth when measured from its base on the ocean floor to its summit, making it taller than Mount Everest, though most of it is hidden beneath the waves. These volcanoes typically have less explosive eruptions because their lava is more fluid and gases can escape more easily. Cinder cone volcanoes are another fascinating type, though they are usually much smaller than their cousins. These form when volcanic material is ejected into the air and falls back to the ground around the vent, creating a circular or oval cone. They have steep sides and are made mostly of loose volcanic fragments called cinders. Paracutin in Mexico is a famous example that appeared suddenly in a farmer's cornfield in 1943 and grew to over 1,000 feet high in just 1 year. Watching it grow was an incredible opportunity for scientists to study how volcanoes form from the very beginning. Magma and lava are terms that people often use interchangeably, but they actually refer to different things. Magma is the molten rock that exists beneath the Earth's surface, while lava is what we call that same molten rock once it erupts and flows on the surface. The difference in names reflects the different environments and behaviors. Magma underground is often under tremendous pressure and contains dissolved gases, while lava at the surface has released much of its gas and behaves differently as it interacts with air and water. The composition of magma varies greatly and determines how explosive an eruption will be and what the lava will look like when it flows. The temperature of lava is absolutely scorching, typically ranging from about 1,300 to 2,200 degrees Fahrenheit, though some special types can be even hotter. At these temperatures, lava glows bright orange or red, and it can melt almost anything it touches. Different types of lava have different properties based on their chemical composition. Basaltic lava, which is low in silica, flows easily and can travel long distances before cooling. This is the type of lava you typically see in Hawaii, where you can sometimes watch it flow like a glowing river. In contrast, rhyolitic lava is high in silica and is thick and sticky like molten glass, barely flowing at all and often plugging up the volcano's vent, which can lead to explosive eruptions when the pressure becomes too great. The gases trapped in magma play a crucial role in volcanic eruptions. The main gases are water vapor, carbon dioxide, and sulfur dioxide, though there are many others present in smaller amounts. When magma rises toward the surface, the pressure decreases, and these dissolved gases begin to form bubbles, much like when you open a bottle of soda and the carbon dioxide forms bubbles and fizz. If the magma is thin and runny, these gas bubbles can escape relatively easily, resulting in gentle eruptions with flowing lava. However, if the magma is thick and sticky, gas bubbles cannot escape easily, and pressure builds up until it results in a violent explosion that can blow the top off the mountain and send ash and rock miles into the sky. Volcanic eruptions are measured using something called the Volcanic Explosivity Index, or VEI, which ranks eruptions on a scale from 0 to 8 based on how much material is ejected and how high the eruption column reaches. A VEI of 0 or 1 represents a gentle effusive eruption with mostly flowing lava and little ash. At the other end of the scale, a VEI of 8 represents a supereruption that ejects more than 1,000 cubic kilometers of material and can have global climatic effects. Thankfully, supereruptions are extremely rare, occurring perhaps only once every 50,000 to 100,000 years on average, though the timing is not regular or predictable. Mount Vesuvius in Italy is one of the most famous volcanoes in history because of its devastating eruption in 79 AD that destroyed the Roman cities of Pompeii and Herculaneum. The eruption buried these cities under layers of ash and pumice, preserving them in remarkable detail for nearly 2,000 years. When archaeologists began excavating Pompeii in the 18th century, they found buildings, artwork, everyday objects, and even the forms of people frozen in their final moments. This tragic event has given us an incredible window into daily life in ancient Rome, but it also serves as a powerful reminder of the destructive power of volcanoes. The eruption happened so quickly that many people did not have time to escape, and it is estimated that thousands died from the pyroclastic flows and ash fall. The eruption of Mount Vesuvius was what scientists now call a Plinian eruption, named after Pliny the Younger, who witnessed and wrote about the disaster. Plinian eruptions are extremely powerful and characterized by enormous eruption columns that can reach into the stratosphere. These eruptions release vast amounts of pumice and ash, and they can produce devastating pyroclastic flows that race down the slopes of the volcano at terrifying speeds. The eruption column from Vesuvius in 79 AD is estimated to have reached about 20 miles high, and the pyroclastic flows that destroyed Pompeii moved at speeds of over 100 miles per hour, with temperatures of about 1,800 degrees Fahrenheit. Krakatoa, a volcanic island in Indonesia, produced one of the most violent eruptions in recorded history in 1883. The explosion was so powerful that it was heard 3,000 miles away, and the shock wave from the blast traveled around the world 7 times. The eruption generated massive tsunamis that killed tens of thousands of people along the coasts of Java and Sumatra. The force of the explosion was equivalent to 200 megatons of TNT, about 13,000 times the power of the atomic bomb dropped on Hiroshima. The eruption also ejected so much ash and sulfur dioxide into the atmosphere that it affected global climate for years, causing spectacular sunsets around the world and lowering global temperatures by more than 1 degree Celsius. Mount St. Helens in Washington state gave scientists and the world a dramatic demonstration of volcanic power in 1980. After being dormant for 123 years, the volcano awakened with a series of small earthquakes and steam eruptions. On May 18, 1980, a massive landslide triggered by an earthquake removed the entire north face of the mountain, suddenly releasing the pressure on the magma inside. This resulted in a lateral blast that devastated an area of over 200 square miles, flattening forests and killing 57 people. The eruption column reached 15 miles high, and ash fell across several states. The power of the blast was equivalent to about 24 megatons of TNT, or roughly 1,600 times the power of the Hiroshima atomic bomb. Mount St. Helens lost over 1,300 feet of elevation in the eruption, dramatically changing its appearance. Iceland sits astride the mid-Atlantic ridge, a boundary between two tectonic plates that are moving apart from each other. This makes Iceland one of the most volcanically active places on Earth, with an eruption occurring somewhere on the island roughly every 4 years on average. The island itself is essentially made entirely of volcanic rock that has accumulated over millions of years as lava erupted from the spreading plate boundary. Icelanders have learned to live with their fiery neighbors, and they even harness the volcanic heat for geothermal energy, which provides heating and electricity for much of the country. The volcanic soil, while sometimes challenging, is also rich in minerals and supports agriculture despite Iceland's northern location. The eruption of Eyjafjallajökull in Iceland in 2010 might not have been particularly large or deadly, but it had outsized impacts on the modern world. The volcano erupted beneath a glacier, and the interaction between the hot lava and the ice created a massive plume of very fine ash that rose high into the atmosphere. This ash posed a serious hazard to aircraft engines, leading to the closure of much of European airspace for nearly a week. Over 100,000 flights were canceled, stranding millions of passengers and causing billions of dollars in economic losses. The event highlighted how even moderate volcanic eruptions can have far-reaching consequences in our interconnected world, disrupting global travel and trade. The Ring of Fire is a horseshoe-shaped belt around the Pacific Ocean, where most of the world's volcanoes are located. This zone is home to about 75% of the world's active volcanoes, and is also where about 90% of the world's earthquakes occur. The Ring of Fire exists because the Pacific Plate and several other oceanic plates are being subducted beneath the continental plates that surround the Pacific Ocean. As these oceanic plates descend into the mantle, they melt and create the magma that feeds the volcanoes. Countries along the Ring of Fire, including Japan, Indonesia, the Philippines, New Zealand, Chile, and the western United States, must live with the constant threat of volcanic eruptions and earthquakes. Indonesia has more active volcanoes than any other country, with over 120 active volcanoes spread across its thousands of islands. This incredible volcanic activity is due to Indonesia's position along the Ring of Fire, where the Australian and Pacific plates are being subducted beneath the Eurasian plate. While these volcanoes pose significant hazards to the millions of people who live nearby, they also bring benefits. The volcanic soil is incredibly fertile, supporting agriculture that feeds much of the population. The volcanoes also create dramatic landscapes that attract tourists from around the world. And geothermal energy from volcanic heat is increasingly being harnessed for electricity generation. Mount Pinatubo in the Philippines had been quiet for over 500 years when it awakened in 1991, with what would become the second largest volcanic eruption of the 20th century. The eruption ejected about 10 cubic kilometers of material and sent an ash column 22 miles high. Fortunately, scientists were able to monitor the volcano's increasing activity and convinced authorities to evacuate over 60,000 people from the surrounding areas, saving countless lives. Despite the successful evacuation, around 800 people died, many from roofs collapsing under the weight of wet ash. The eruption had significant global climatic effects, with sulfur dioxide forming a haze in the stratosphere that lowered global temperatures by about 0.5 degrees Celsius for several years, and caused spectacular sunsets worldwide. Volcanoes under the ocean are even more numerous than those on land, though they are less well known because we cannot see them. Mid-ocean ridges, where tectonic plates are pulling apart, are lined with underwater volcanoes that are constantly erupting and creating new oceanic crust. In fact, most of the volcanic activity on Earth happens underwater. These submarine volcanoes can eventually grow tall enough to break the surface and form new islands. The Hawaiian Islands are a perfect example of this process, with each island representing a volcano that grew from the seafloor to above sea level over millions of years. Even today, there is a new underwater volcano called Loihai growing off the coast of the big island of Hawaii, though it will not reach the surface for tens of thousands of years. Hydrothermal vents, also called black smokers, are found near underwater volcanoes and are some of the strangest and most fascinating environments on Earth. These vents occur where seawater seeps into cracks in the ocean floor near volcanic activity, gets superheated by magma, and then shoots back out into the cold ocean water. The water coming from these vents can be over 700 degrees Fahrenheit, and it is loaded with minerals and chemicals. When this hot, mineral-rich water meets the cold ocean water, the minerals precipitate out and form chimney-like structures that can grow quite tall. Remarkably, these vents support entire ecosystems of creatures that survive without sunlight, instead relying on bacteria that can metabolize the chemicals from the vents. The discovery of life around hydrothermal vents in the late 1970s revolutionized our understanding of where life can exist. Scientists found giant tube worms, strange clams, blind shrimp, and many other creatures thriving in these extreme environments. These organisms do not depend on photosynthesis like most life on Earth, but instead rely on chemosynthesis, where bacteria convert the chemicals from the vents into energy. This discovery has profound implications for the search for life on other planets and moons, suggesting that life might exist in places we previously thought were too hostile, such as beneath the ice on Jupiter's moon Europa or Saturn's moon Enceladus. Volcanic islands like Hawaii are formed by hotspots, which are areas where magma from deep in the mantle rises in a stationary plume to the surface. As a tectonic plate moves over this hotspot, it creates a chain of volcanoes, with the youngest and most active volcano sitting directly over the hotspot. In Hawaii, the Big Island is currently over the hotspot and has active volcanoes, while the older islands to the northwest are extinct and gradually eroding away. Over millions of years, this process has created the entire Hawaiian island chain, stretching for over 1,500 miles across the Pacific Ocean. The islands get progressively older as you move northwest, with the oldest islands now eroded into tiny atolls and seamounts. Yellowstone National Park in the United States sits atop one of the world's largest supervolcanoes, though most visitors are unaware of the enormous volcanic system beneath their feet. The Yellowstone caldera is about 34 by 45 miles across and was created by massive eruptions that occurred roughly 2.1 million, 1.3 million, and 640,000 years ago. Each of these eruptions ejected hundreds to thousands of cubic kilometers of material, making them some of the largest volcanic events in Earth's history. The volcanic activity beneath Yellowstone is responsible for the park's famous geothermal features, including Old Faithful Geyser, hot springs, mud pots, and fumaroles. Scientists carefully monitor the volcano for any signs of awakening, though there is no indication that an eruption is imminent, and the probability of a major eruption in any given year is very low. Volcanic ash is not like the soft, fluffy ash from a wood fire, but is instead made of tiny, sharp fragments of volcanic glass and rock. These particles are created when magma is explosively fragmented during an eruption, with gas bubbles in the magma shattering it into countless tiny pieces. Under a microscope, volcanic ash particles look like tiny shards of glass with jagged edges. This makes volcanic ash particularly dangerous to breathe, as it can damage lungs and cause respiratory problems. Ash is also problematic for many other reasons. It can collapse roofs when it accumulates, contaminate water supplies, damage crops, disrupt transportation, and cause electrical equipment to fail. Even small amounts of ash can cause problems for aircraft engines, which is why ash clouds from volcanic eruptions lead to flight cancellations. Pumice is a volcanic rock so light that it actually floats on water. This strange rock forms when lava with high gas content erupts and cools so quickly that the gas bubbles are trapped inside, creating a rock that is full of tiny holes, like a frozen foam. Some pumice is so full of holes that it contains more air than rock. Large volcanic eruptions can produce enormous amounts of pumice that forms rafts on the ocean, sometimes miles across, that drift with currents for years. These pumice rafts can transport organisms across vast distances and even pose hazards to ships. Ancient peoples valued pumice for its ability to smooth and polish surfaces, and it is still used today in various applications, from cosmetics to construction. Obsidian is another type of volcanic rock that has captivated humans for thousands of years. This rock forms when lava cools so rapidly that crystals do not have time to form, resulting in volcanic glass. Obsidian is typically black, though it can also be red, brown, or even striped with different colors. It fractures into extremely sharp edges, sharper than even steel or glass, which made it prized by ancient peoples for making cutting tools, arrowheads, and knives. Some cultures traded obsidian over long distances, and archaeologists can sometimes trace ancient trade routes by analyzing the chemical composition of obsidian artifacts and matching them to their source volcanoes. Even today, some surgeons use obsidian scalpel blades because they can be sharper than steel. The fertile soil created by weathered volcanic material is one of the great benefits that volcanoes provide. Volcanic rock is rich in minerals, including potassium, phosphorus, and many trace elements that plants need to grow. When volcanic material weathers and breaks down over time, it creates some of the most fertile soil on the planet. This is why many volcanic regions, despite the dangers, have high population densities and intensive agriculture. The soils around Mount Vesuvius in Italy, in the highlands of Java in Indonesia, and in the Rift Valley of East Africa are all incredibly productive due to their volcanic origins. This fertility has drawn people to live in the shadow of dangerous volcanoes throughout human history, weighing the risks against the benefits that volcanic soil provides. Coffee lovers owe a debt to volcanoes because many of the world's best coffee growing regions are located on volcanic slopes. The volcanic soil provides the minerals that coffee plants need, and the mountainous terrain of volcanic regions offers the elevation and climate that produces high-quality coffee beans. Famous coffee-growing regions like the Kona district of Hawaii, the highlands of Guatemala, parts of Indonesia, and regions of Colombia and Ethiopia all benefit from volcanic soils. The same is true for many other crops, including wine grapes, which thrive in volcanic soils in regions like Mount Etna in Sicily, the Canary Islands, and parts of California. Geothermal energy is one of the most sustainable and reliable forms of renewable energy, and it is closely connected to volcanic activity. In areas with volcanic heat close to the surface, water can be pumped down into hot rocks where it is heated and then brought back to the surface as steam or hot water. This heat can be used directly for heating buildings or for generating electricity by driving turbines. Countries like Iceland, New Zealand, Kenya, and the Philippines generate significant portions of their electricity from geothermal sources. In Iceland, nearly all homes are heated with geothermal energy, and about 25% of the country's electricity comes from geothermal power plants. This clean, reliable energy source is available 24 hours a day, unlike solar or wind power, making it especially valuable. Volcanic gases can be both dangerous and important for understanding volcanic activity. The main gas released by volcanoes is water vapor, but volcanoes also emit carbon dioxide, sulfur dioxide, hydrogen sulfide, and many other gases. Carbon dioxide is heavier than air and can accumulate in low-lying areas, displacing oxygen and causing suffocation. In 1986, a sudden release of carbon dioxide from Lake Nyos in Cameroon, a lake sitting in a volcanic crater, killed over 1,700 people and thousands of animals as the dense gas flowed down valleys. Sulfur dioxide can react with water in the atmosphere to form sulfuric acid, which falls as acid rain. However, by monitoring changes in the types and amounts of gases a volcano emits, scientists can often detect when magma is rising and predict when eruptions might occur. Pyroclastic flows are among the most deadly volcanic hazards, and understanding them is crucial for anyone living near an active volcano. These flows are superheated mixtures of gas, ash, and rock fragments that race down the slopes of volcanoes at speeds that can exceed 450 miles per hour. The temperature inside a pyroclastic flow can reach 1,800 degrees Fahrenheit or even higher, hot enough to incinerate virtually anything in its path. What makes these flows so dangerous is their speed and density. They hug the ground and follow valleys, meaning they can travel much farther than you might expect. There is essentially no way to outrun a pyroclastic flow once it starts, which is why early warning and evacuation are so critical in volcanic areas. The citizens of St. Pierre on the Caribbean island of Martinique learned the devastating power of pyroclastic flows in the most tragic way possible. In 1902, Mount Pelée began showing signs of unrest, but authorities were reluctant to order evacuations, partly because an election was scheduled. On May 8, 1902, the volcano produced a massive pyroclastic flow that swept down the mountain and completely destroyed the city of St. Pierre in minutes. Of the approximately 28,000 people in the city, only 2 survived. One was a prisoner who was protected by the thick walls of his underground cell. The ships in the harbor were capsized or set on fire, and the city was left in ruins. This disaster led to major advances in the study of pyroclastic flows, and this type of flow is sometimes called a Pelion eruption in memory of this tragedy. Lahars are another deadly volcanic hazard that can occur during eruptions or even long after volcanic activity has ceased. These are rapidly flowing mixtures of water and volcanic debris that resemble rivers of concrete, carrying boulders, trees, and anything else in their path. Lahars can be triggered when volcanic material mixes with water from heavy rainfall, melting snow and ice, or from a crater lake. They follow river valleys and can travel for dozens of miles from a volcano, moving at speeds up to 60 miles per hour. In 1985, a relatively small eruption of Nevado del Ruiz in Colombia melted glaciers on the summit, creating massive lahars that buried the town of Armero and killed over 23,000 people. The tragedy was compounded by inadequate warnings and delays in evacuation orders, despite scientists having predicted the danger. The 1815 eruption of Mount Tambora in Indonesia was the largest volcanic eruption in recorded history, with a VEI of 7. The eruption ejected an estimated 160 cubic kilometers of material into the atmosphere and killed at least 71,000 people directly through pyroclastic flows, ashfall, and tsunamis. However, the global impact was even more devastating. The enormous amount of sulfur dioxide and ash injected into the stratosphere created a veil that blocked sunlight around the world. The year 1816 became known as the year without a summer in Europe and North America, with snow falling in June, crop failures, and widespread food shortages. This climatic disruption led to famine, disease, and social unrest in many parts of the world. The eruption even influenced culture, as the cold, dark summer of 1816 kept Mary Shelley and her companions indoors at Lake Geneva, where she wrote her famous novel Frankenstein. Volcanoes have played a crucial role in making Earth habitable for life as we know it. In the early history of our planet, billions of years ago, volcanic outgassing released enormous amounts of water vapor, carbon dioxide, nitrogen, and other gases that formed Earth's early atmosphere. The water vapor eventually condensed to form the oceans. Without this volcanic activity, Earth would have no atmosphere or water, making life impossible. Even today, volcanoes continue to recycle materials between the interior and surface of the planet, playing an essential role in the carbon cycle and other geochemical processes that maintain Earth's habitability. The carbon dioxide released by volcanoes over geological time has been balanced by processes that remove it from the atmosphere, helping to regulate Earth's climate over millions of years. The question of whether we can predict volcanic eruptions is one that scientists have been working on for decades. Unlike weather forecasting, which has become quite accurate for short periods, predicting volcanic eruptions remains challenging. However, volcanoes typically give warning signs before they erupt. These signs include increased earthquake activity, as magma moves underground, ground deformation. As magma pushes up the surface, changes in gas emissions, and changes in temperature of hot springs and fumaroles. By monitoring these signs with networks of seismometers, GPS stations, gas sensors, and satellite observations, scientists can often predict that an eruption is likely within days or weeks. However, predicting the exact timing, size, and nature of an eruption remains difficult, and sometimes volcanoes produce warning signs without erupting, or they erupt with little warning. The Hawaiian Volcano Observatory, established in 1912, was one of the first permanent volcano monitoring stations in the world, founded by Thomas Jagger, a professor from MIT who was inspired to study volcanoes after witnessing the aftermath of the Mount Pelée disaster. The observatory has been continuously monitoring Kilauea and Mauna Loa for over a century. The long-term monitoring has provided invaluable data about how these shield volcanoes behave, allowing scientists to develop better methods for predicting eruptions. Kilauea, one of the most active volcanoes in the world, erupted almost continuously from 1983 to 2018, providing scientists with an unparalleled opportunity to study an active volcano up close. The 2018 eruption of Kilauea was particularly notable, as it destroyed over 700 homes and dramatically changed the landscape of the lower Puna district. Volcanoes exist on other planets and moons in our solar system, revealing that volcanic activity is common throughout our celestial neighborhood. Mars has Olympus Mons, the largest volcano in the solar system, standing about 13.6 miles high and 370 miles across at its base. That is nearly 3 times the height of Mount Everest. Olympus Mons is a shield volcano like those in Hawaii, but on a massive scale. It formed over hundreds of millions of years as lava flows slowly built up the mountain. The volcano is currently dormant, but scientists believe it could have been active within the past few million years, which is recent in geological terms. The enormous size of Martian volcanoes compared to those on Earth is partly because Mars lacks plate tectonics, so hotspots remain in the same place for very long periods, allowing volcanoes to grow much larger. Jupiter's moon Io is the most volcanically active body in the solar system, with hundreds of active volcanoes covering its surface. The volcanic activity on Io is not driven by internal heat left over from formation or by radioactive decay as on Earth, but rather by tidal heating. Jupiter's immense gravity, along with gravitational tugs from other large moons, constantly flexes and squeezes Io, generating tremendous heat through friction. This heat melts rock in Io's interior, creating magma that erupts in spectacular volcanic plumes that can reach over 200 miles high, shooting material into space. Some of these volcanic eruptions are so powerful that they can be observed from Earth with large telescopes. The surface of Io is constantly being resurfaced by volcanic activity, making it one of the youngest surfaces in the solar system with no visible impact craters. Saturn's tiny moon Enceladus is another world with volcanic activity, though of a very different type than we see on Earth or Io. Enceladus has ice volcanoes, or cryovolcanoes, that erupt water and ice instead of molten rock. The Cassini spacecraft observed enormous plumes of water vapor and ice particles shooting from cracks near Enceladus's south pole. These plumes contain organic molecules and salts, suggesting that there is a liquid water ocean beneath the icy surface. The discovery of these cryovolcanoes has made Enceladus one of the most promising places to search for extraterrestrial life in our solar system. Energy source for this activity appears to be tidal heating from Saturn's gravity, similar to what powers the volcanoes on Io. Venus, Earth's sister planet, has more volcanoes than any other planet in the solar system, with thousands dotting its surface. Radar mapping by spacecraft has revealed massive shield volcanoes, volcanic plains covering vast areas, and strange circular features called coronae that may be unique to Venus. However, we are not sure how active Venusian volcanism is today. Recent observations have detected changes in sulfur dioxide levels in Venus's atmosphere and possible heat signatures that could indicate recent eruptions. But without a dedicated mission to Venus with modern instruments, the level of current activity remains uncertain. The entire surface of Venus appears to have been resurfaced by massive volcanic activity about 300 to 500 million years ago. But whether this was a catastrophic global event or occurred gradually over time is still debated by scientists. Volcanic lightning is one of the most spectacular and mysterious phenomena associated with eruptions. During explosive eruptions, the rising ash column becomes charged with static electricity through the collision of ash particles, ice, and rock fragments. When the charge separation becomes great enough, lightning bolts flash through the eruption column and between the column and the ground. These lightning storms within volcanic plumes can be incredibly intense, with thousands of lightning strikes occurring during a single eruption. Scientists are still working to fully understand the physics behind volcanic lightning, but studying it can provide insights into the dynamics of eruption columns and the processes happening inside them. Photographs of volcanic lightning are among the most dramatic images of eruptions, showing brilliant bolts of electricity against the backdrop of glowing lava and dark ash. The ancient Greeks believed that volcanoes were the forges of Hephaestus, their god of fire and metalworking, similar to the Roman god Vulcan. Different cultures around the world have developed their own myths and legends to explain volcanic activity. In Hawaiian mythology, the volcano goddess Pele is believed to live in Halem, a letter 2BB, UM, a letter 2BB crater at the summit of Kilauea. Native Hawaiians have traditionally left offerings to Pele and have many stories about her fiery temper and her conflicts with other gods. In Japanese mythology, Mount Fuji is considered sacred and has been a place of pilgrimage for centuries. These cultural connections to volcanoes reflect how deeply volcanic activity has influenced human societies, inspiring both fear and reverence. The word lava itself comes from Italian and was first used to describe the molten rock flowing from Mount Vesuvius. Similarly, many volcanic terms we use today have Italian origins because Italy has been home to extensive volcanic activity, and because Italian scientists made many early contributions to volcanology. Terms like volcano, magma, fumarole, and caldera all have Italian or Latin roots. This linguistic heritage reflects the long history of Italians living alongside active volcanoes like Vesuvius, Etna, and Stromboli, observing and trying to understand these fiery mountains. Stromboli, a small volcanic island off the coast of Italy, has been erupting almost continuously for at least 2,000 years, and possibly much longer. The eruptions occur regularly, every 15 to 20 minutes, as gas-rich magma rises to the surface and bursts through the lava surface, throwing incandescent blobs of lava into the air. This regular activity has earned Stromboli the nickname Lighthouse of the Mediterranean, because sailors have long used the glow from its eruptions for navigation at night. The style of eruption exhibited by Stromboli is so characteristic that volcanologists use the term Strombolian eruption to describe similar activity at other volcanoes around the world. Despite its constant activity, Stromboli is inhabited, with several hundred people living on the island, and tourists regularly hiking to the summit to watch the eruptions. Mount Etna in Sicily is Europe's tallest active volcano and one of the most active volcanoes in the world. The mountain has been erupting for hundreds of thousands of years, and historical records document eruptions going back over 2,500 years. Etna's frequent eruptions have shaped the landscape and culture of eastern Sicily, with lava flows periodically threatening towns and cities on its slopes. The volcano has different summit craters that take turns being active, and it also produces eruptions from vents on its flanks. Despite the constant threat, the slopes of Etna are densely populated because the volcanic soil is incredibly fertile. The mountain is also a tourist attraction, with thousands of visitors coming each year to see the active craters and dramatic volcanic landscapes. Calderas are among the most impressive volcanic features on Earth. These large depressions form when a volcano erupts so much material that the ground above the emptied magma chamber collapses, creating a huge basin. Calderas can be miles across and form in massive eruptions that eject tens or hundreds of cubic kilometers of material. Crater Lake in Oregon sits in a caldera that formed about 7,700 years ago when Mount Mazama erupted and collapsed. The eruption was one of the largest in North America in the past 10,000 years, and the caldera later filled with water to form the deep blue lake we see today. Similar caldera lakes exist around the world, and they are often popular tourist destinations because of their dramatic beauty. The supervolcano beneath Lake Toba in Indonesia produced the largest known volcanic eruption in the past 2 million years. About 74,000 years ago, Toba erupted and ejected an estimated 2,800 cubic kilometers of material, making it a VEI-8 eruption. The eruption created a caldera that is now filled by Lake Toba, which is about 60 miles long and 20 miles wide. The climatic effects of this eruption were severe, with some scientists suggesting it caused a volcanic winter that lasted for years and may have pushed humanity to the brink of extinction. Genetic studies suggest that the human population may have been reduced to as few as 3,000 to 10,000 individuals during this time, creating a population bottleneck. However, this theory remains controversial, and not all scientists agree that the Toba eruption had such dramatic effects on human populations. Volcanic winters occur when massive eruptions inject so much ash and sulfur dioxide into the stratosphere that they block a significant amount of sunlight from reaching Earth's surface. The sulfur dioxide forms tiny droplets of sulfuric acid that can remain suspended in the stratosphere for years, creating a haze that reflects sunlight back into space. This can lower global temperatures by several degrees, disrupt weather patterns, and cause crop failures. The effects of volcanic winters have been documented after many large historical eruptions, including Tambora in 1815 and Krakatoa in 1883. Scientists study ancient eruptions preserved in ice cores and geological records to understand how volcanic winters have affected climate throughout Earth's history. Ice cores from Greenland and Antarctica provide a remarkable record of past volcanic eruptions going back hundreds of thousands of years. When a volcano erupts and sends sulfur dioxide into the stratosphere, it eventually falls as sulfuric acid in snow. Scientists can drill cores through the ice sheets and analyze the chemical composition of ice formed in different years. Spikes in sulfur content mark major volcanic eruptions, and by dating the ice, scientists can determine when these eruptions occurred. This record reveals that large volcanic eruptions have been much more common throughout history than written records alone would suggest, and it helps scientists understand the frequency and impact of major eruptions. The volcanic arc of the Andes Mountains in South America is one of the most spectacular examples of volcanoes formed by subduction. As the Nazca Oceanic Plate subducts beneath the South American continental plate, it creates a chain of volcanoes running the length of the continent. This volcanic arc includes some of the world's highest volcanoes, with several peaks exceeding 20,000 feet in elevation. The combination of volcanic activity and the mountain building from the plate collision has created the dramatic landscape of the Andes. Countries like Chile, Ecuador, and Peru must contend with numerous active volcanoes, but they also benefit from geothermal energy, mineral deposits associated with volcanic activity, and dramatic scenery that attracts tourists. Nevado Ojos del Salado, on the border between Chile and Argentina, is the world's highest volcano at 22,615 feet above sea level. This massive stratovolcano sits in the high, dry Andes, where the thin air and cold temperatures preserve the mountain's glaciers despite being located in a relatively low latitude. The volcano is considered active, though its last confirmed eruption was over 1,000 years ago. Climbing this giant requires dealing with extreme altitude, cold, and the challenges of reaching such a remote location. The height of Nevado Ojos del Salado and other Andean volcanoes is partly due to the thick continental crust of South America, which allows volcanic mountains to be built higher than they could be on oceanic crust. The East African Rift is a place where a continent is literally being torn apart, and volcanic activity is one of the most obvious signs of this tectonic drama. The rift runs from the Afar region in Ethiopia southward through Kenya, Tanzania, and into Mozambique, a distance of over 3,000 miles. As the African continent splits, the crust stretches and thins, allowing magma to rise more easily to the surface. This has created numerous volcanoes along the rift, including famous peaks like Mount Kilimanjaro, Mount Kenya, and Al Doinio Lengai. The Rift Valley also features beautiful rift lakes, geothermal areas, and dramatic escarpments. In millions of years, if the rifting continues, this region will likely split entirely, and a new ocean will form between two separate continents. Al Doinio Lengai in Tanzania is one of the most unusual volcanoes on Earth because it erupts carbonatite lava, a type of lava with a very different chemical composition than typical volcanic rocks. Carbonatite lava is extremely fluid and has a low eruption temperature of only about 900 to 1,100 degrees Fahrenheit, much cooler than basaltic lava. When it erupts at night, it glows dull red, but is almost invisible during the day because it is not hot enough to glow brightly. After erupting, carbonatite lava is black, but quickly turns white as it reacts with moisture in the air, giving the volcano's summit a snow-like appearance despite being located near the equator. The name Al Doinio Lengai means Mountain of God in the Maasai language, and the volcano is sacred to the local Maasai people. Mount Erebus in Antarctica is the southernmost active volcano on Earth, sitting on Ross Island in the Antarctic Ross Sea. This stratovolcano rises to 12,448 feet and is notable for having a persistent lava lake in its summit crater, one of only a few volcanoes in the world with such a feature. The combination of extreme cold and volcanic heat creates unique conditions, with ice caves and fumaroles producing ice towers called ice chimneys that can be dozens of feet tall. Scientists maintain a research station near Mount Erebus to study the volcano and the unique environment it creates. The volcano's location makes it a challenging but scientifically valuable place to study volcanic processes in an extreme environment. Volcanic bombs are large fragments of molten or semi-molten rock ejected during explosive eruptions. These can range from fist-sized chunks to blocks weighing several tons. As they fly through the air, volcanic bombs can take on distinctive shapes. Some cool and form a smooth, aerodynamic shape, while others remain molten on the outside and develop twisted or ribbon-like forms. Bread crust bombs have a cracked surface resembling bread crust, formed when the outer surface cools and solidifies, while the interior continues to expand. Volcanic bombs can be ejected several miles from the vent, and they pose a serious hazard to anyone near an erupting volcano. Finding volcanic bombs from ancient eruptions helps scientists understand the nature and violence of past volcanic events. The island of Surtsey emerged from the sea off the coast of Iceland between 1963 and 1967 during a dramatic submarine volcanic eruption. The eruption began 425 feet below sea level, and within days, the volcano had built itself above the waves, creating a new island. The explosive interaction between the hot lava and cold seawater created spectacular eruptions of steam, ash, and rock that could be seen from the Icelandic mainland. By the time the eruption ended, Surtsey covered about 1.3 square miles. Since then, erosion has reduced its size, but the island remains an important natural laboratory where scientists study how life colonizes new land. Access to Surtsey is strictly controlled to avoid human interference with this natural colonization process, making it one of the few pristine natural laboratories in the world. Volcanic soils, known as andesols, have unique properties that make them excellent for agriculture, despite the dangers posed by the volcanoes that create them. These soils form from weathered volcanic ash and other volcanic materials, and they are typically rich in minerals, while also having good water retention and drainage properties. The dark color of many volcanic soils helps them warm quickly in the sun, extending growing seasons in cooler climates. Some of the world's most productive agricultural regions are found on volcanic soils, supporting crops ranging from rice and tea in Asia to coffee in Central America and wine grapes in volcanic regions worldwide. The fertility of volcanic soils is one of the main reasons why people continue to live in the shadow of dangerous volcanoes. Monitoring volcanoes has become increasingly sophisticated with modern technology, allowing scientists to detect subtle changes that might indicate an impending eruption. Seismometers detect the tiny earthquakes caused by magma moving underground, with characteristic patterns often developing as an eruption approaches. GPS stations measure ground deformation with millimeter precision, detecting the swelling that occurs when magma accumulates beneath a volcano. Gas sensors analyze the composition and quantity of gases being released, with changes often indicating that fresh magma is rising toward the surface. Satellite observations can detect heat, ground deformation, and gas emissions from space, allowing monitoring of even the most remote volcanoes. Scientists also use techniques like measuring gravity changes, electrical conductivity variations, and acoustic monitoring to build a comprehensive picture of what is happening inside a volcano. The concept of volcanic risk involves both the hazard posed by a volcano and the vulnerability of populations living nearby. A very active volcano in a remote area might pose little risk because few people are exposed to its hazards, while even a relatively quiet volcano near a major city represents a significant risk. Scientists work to create hazard maps showing which areas are most likely to be affected by lava flows, pyroclastic flows, ash fall, and lahars. These maps help governments and communities plan for volcanic emergencies and make decisions about land use. However, balancing volcanic risk with the benefits of living near volcanoes, such as fertile soil and geothermal energy, remains a challenge for millions of people worldwide. Education about volcanic hazards and establishing early warning systems are crucial for reducing the risk to communities. Volcanic ash clouds pose a serious threat to aviation, as demonstrated repeatedly over the past few decades. When jet engines ingest volcanic ash, the tiny glass particles can melt in the hot engine and then solidify on cooler surfaces, potentially causing engines to fail. Ash can also damage the aircraft's windscreen, contaminate fuel systems, and interfere with instruments. Several incidents have involved aircraft flying through ash clouds and experiencing multiple engine failures, though fortunately, in most cases, pilots were able to restart engines and land safely. After the Eyjafjallajökull eruption in 2010 disrupted European aviation, international efforts were made to improve volcanic ash detection and forecasting. Specialized centers now monitor volcanic activity globally and issue warnings to aviation authorities when ash clouds could affect flight routes. Phrase volcanic neck refers to the hardened magma plug that filled the conduit of an ancient volcano. Over millions of years, the softer surrounding rock erodes away, leaving the more resistant volcanic neck standing as a prominent landmark. Ship Rock in New Mexico is a famous example, rising dramatically 1,583 feet above the surrounding desert landscape. This volcanic neck formed about 30 million years ago when magma solidified in the throat of a volcano. The softer volcanic cone has long since eroded away, leaving only this spectacular tower of dark volcanic rock that was sacred to the Navajo people. Similar volcanic necks can be found around the world, standing as monuments to volcanoes that died millions of years ago. Pahoehoe and Ah are two Hawaiian words that have been adopted by geologists worldwide to describe different types of basaltic lava flows. Pahoehoe lava has a smooth, ropey surface that forms when the thin, fluid lava develops a flexible skin that wrinkles as the lava continues to flow beneath it. Walking on cooled Pahoehoe is relatively easy, as the surface is smooth, though you need to watch for thin crusts over lava tubes. Lava, in contrast, has a rough, jagged surface made of sharp, broken chunks of lava. The difference between Pahoehoe and is mainly due to how much the lava has been disturbed and how much gas it has lost. A flow can start as Pahoehoe and transform into as it moves downslope and loses gas. Walking on is treacherous and exhausting, as each step requires carefully placing your feet among sharp, unstable rocks. Lava tubes are fascinating features that form when a lava flow develops a solid crust on top, while the molten interior continues to flow. Once the eruption stops and the lava drains out, it leaves behind a hollow tunnel through the solidified rock. Some lava tubes are small passages you must crawl through, while others are enormous caverns tall enough to fit a house inside. The longest known lava tube system on the Big Island of Hawaii extends for over 40 miles. Lava tubes are important because they allow lava to travel much farther from the vent than it otherwise could, insulated from cooling by the surrounding rock. These tubes can remain at stable temperatures year-round, and some have been proposed as potential sites for human habitats on the Moon or Mars, where they could provide protection from radiation and extreme temperatures. Pillow lava forms when lava erupts underwater, creating distinctive rounded shapes that do indeed resemble stacks of pillows. When hot lava meets cold water, the outer surface chills instantly into glass, forming a skin. The pressure of more lava inside breaks through this skin, and a new pillow bulges out and is similarly chilled. This process repeats, creating a pile of interconnected pillow-shaped structures. Finding pillow lavas in ancient rocks that are now on land tells geologists that those rocks formed underwater, even if they are now high in mountains. The study of pillow lavas has helped scientists understand plate tectonics and the history of ocean basins. Divers and submarines have filmed pillow lavas forming during underwater eruptions, providing dramatic footage of a process that usually happens in the dark depths. Volcanic tremor is a distinctive type of seismic signal that differs from normal earthquakes. Instead of the sharp jolts of typical earthquakes, volcanic tremor consists of continuous, rhythmic vibrations that can last for hours, days, or even months. Scientists think volcanic tremor is caused by magma and volcanic gases moving through cracks and conduits in the volcano, similar to how water flowing through pipes can cause them to vibrate. Different patterns of volcanic tremor are associated with different types of volcanic activity, and monitoring tremor helps scientists understand what is happening inside a volcano. The development of harmonic tremor, a particularly rhythmic type, often indicates that an eruption is imminent as magma rises toward the surface. The viscosity of magma is one of the most important factors determining how a volcano will erupt. Viscosity is essentially how thick or sticky a liquid is. Honey is more viscous than water, for example. Magma viscosity depends primarily on its chemical composition, particularly its silica content and its temperature. Basaltic magma with low silica content and high temperature has low viscosity and flows easily, producing relatively gentle effusive eruptions with flowing lava. Rhyolitic magma with high silica content and lower temperature has high viscosity and barely flows at all, producing explosive eruptions because gases cannot escape easily. Andesitic magma, intermediate in composition, produces intermediate-style eruptions. Understanding magma viscosity helps scientists predict what type of eruption a volcano is likely to produce. The Pacific Ring of Fire contains not only most of the world's volcanoes, but also represents one of the most dynamic geological regions on Earth. The ring is essentially a horseshoe of subduction zones, where oceanic plates dive beneath other plates, creating the conditions for volcanic activity. The western side of the ring, along the coasts of Asia and Oceania, is where the Pacific Plate and several smaller plates subduct beneath the Eurasian, Philippine, and Australian plates. The eastern side, along the Americas, is where the Pacific Plate and smaller oceanic plates subduct beneath the North and South American plates. The northern portion involves the Pacific Plate subducting beneath the North American Plate in Alaska and the Aleutian Islands. This ring of volcanic and seismic activity shapes the lives of hundreds of millions of people living in countries bordering the Pacific Ocean. Mount Rainier in Washington state is considered one of the most dangerous volcanoes in the United States, not because it erupts frequently, but because of its proximity to major population centers. The Seattle-Tacoma metropolitan area, home to millions of people, lies within range of potential lahars from the volcano. Mount Rainier is covered with glaciers, and any significant eruption would almost certainly melt large amounts of ice, generating massive lahars that would flow down river valleys toward populated areas. Geological studies have found evidence of enormous lahars from Mount Rainier that occurred thousands of years ago, some of which reached what is now the site of Tacoma. The volcano last erupted in the mid-1800s, and while it is currently quiet, scientists monitor it carefully because of the potential threat it poses. Communities in the area have developed evacuation plans and warning systems specifically for volcanic hazards from Mount Rainier. The volcanic island arc of Japan is one of the most studied volcanic regions in the world, partly because Japan has excellent scientific infrastructure, and partly because volcanic hazards directly affect one of the world's most populous countries. Japan has over 100 active volcanoes, more than almost any country except Indonesia. Japanese volcanologists have made many contributions to understanding volcanic processes, and Japan has developed sophisticated monitoring networks and hazard mitigation strategies. The country's volcanic activity results from the subduction of the Pacific Plate beneath the North American Plate in the north and the Philippine Sea Plate beneath the Eurasian Plate in the south. Famous Japanese volcanoes include Mount Fuji, which last erupted in 1707, and Sakurajima, which erupts almost daily and is one of the most active volcanoes in the world. Mount Fuji holds a special place in Japanese culture as a sacred mountain and a symbol of Japan itself. This perfectly symmetrical stratovolcano rises 12,389 feet and is visible from Tokyo on clear days. Fuji has been celebrated in Japanese art, poetry, and literature for centuries, most famously in Hokusai's series, 36 Views of Mount Fuji. Thousands of people climb the mountain each summer, with many timing their ascent to watch the sunrise from the summit. Despite its cultural significance and apparent tranquility, Mount Fuji is an active volcano that last erupted in 1707 in what is known as the Hoi eruption. That eruption covered Edo, present-day Tokyo, with several inches of ash and lasted for 2 weeks. Scientists carefully monitor Fuji because a similar eruption today would have severe impacts on the Tokyo metropolitan area, home to over 30 million people. Sakurajima, located in southern Japan near the city of Kagoshima, is one of the most active volcanoes in the world and one of the most closely monitored. The volcano produces frequent small to moderate explosive eruptions, sometimes hundreds per year, sending ash plumes several miles high. Residents of Kagoshima have learned to live with the constant volcanic activity, with ash fall being a regular part of life. People carry umbrellas not just for rain, but to protect against falling ash, and special shelters have been built throughout the area to protect against volcanic bombs. Despite the hazards, people continue to live on and around the volcano, partly because moving would be economically difficult, and partly because it is their home. Sakurajima was originally a separate island, but a major eruption in 1914 produced so much lava that it connected the island to the mainland. Volcanoes can create their own weather systems through the enormous amount of heat and moisture they release. Rising hot air from eruptions creates powerful updrafts that can generate thunderstorms in and around the eruption column. The water vapor and ash create conditions favorable for lightning, and the rapid condensation of moisture can produce torrential rain. This volcanic rain can be beneficial in washing ash from the air more quickly, but it can also mix with ash to create muddy slurries that are difficult to clean and can cause additional damage. The heat from large lava flows can create dust devils and small whirlwinds as hot air rises rapidly. During major eruptions, the effects on local weather can be dramatic and create hazardous conditions beyond the direct volcanic hazards. Volcanic gases released during eruptions can have immediate local effects and longer-term global impacts. Carbon dioxide is colorless and odorless, and because it is heavier than air, it can accumulate in low-lying areas and displace oxygen, creating suffocation hazards. Sulfur dioxide has a sharp, acrid smell and irritates the eyes and respiratory system, but it also plays a role in climate. In the stratosphere, sulfur dioxide reacts with water to form sulfuric acid droplets that reflect sunlight, cooling the climate. Hydrogen sulfide smells like rotten eggs and is toxic even in small concentrations. Hydrogen fluoride and hydrogen chloride are corrosive gases that can damage vegetation and contaminate water supplies. Monitoring these gases helps scientists understand what is happening inside a volcano and provides warning of changes in activity. Volcanic pollution, known as VOG when it refers to volcanic smog, affects communities near active volcanoes. VOG forms when sulfur dioxide and other volcanic gases react with oxygen, moisture, and sunlight in the atmosphere, creating a haze that can reduce visibility and cause respiratory problems. In Hawaii, VOG from Kilauea affected air quality across large parts of the Big Island and sometimes reached other Hawaiian islands hundreds of miles away. People with asthma or other respiratory conditions are particularly vulnerable to VOG. Acid rain from volcanic gases can damage crops, corrode metal surfaces, and acidify water supplies. Despite these problems, communities near volcanoes often develop adaptation strategies and continue to live in these areas because of the many benefits volcanoes provide. The deep carbon cycle involves the movement of carbon between the Earth's surface and its interior over geological time, and volcanoes play a crucial role in this process. Carbon from the atmosphere and oceans becomes incorporated into rocks through various processes, and when oceanic crust subducts into the mantle, it carries this carbon deep into the earth. Some of this carbon returns to the surface through volcanic eruptions, completing the cycle. Over millions of years, this deep carbon cycle has helped regulate Earth's climate by balancing the carbon released by volcanoes with the carbon removed from the atmosphere by weathering and burial in sediments. Understanding this cycle is important for comprehending how Earth's climate has evolved over geological time and remained relatively stable despite the sun gradually becoming brighter over billions of years. Volcanic aerosols are tiny particles and droplets suspended in the atmosphere after eruptions. Sulfuric acid droplets formed from volcanic sulfur dioxide can remain in the stratosphere for several years, spreading around the globe and affecting climate. These aerosols reflect sunlight back into space, cooling the surface. After the 1991 eruption of Mount Pinatubo, global temperatures dropped by about 0.5 degrees Celsius for several years. Scientists have studied volcanic aerosols to understand their effects on climate and weather patterns, including how they might affect monsoons, precipitation patterns, and ocean temperatures. Some scientists have proposed deliberately creating aerosols similar to those produced by volcanoes as a form of solar geoengineering to counteract global warming. though this remains controversial due to potential unintended consequences. The caldera collapse that can occur during major eruptions is a dramatic process that fundamentally reshapes a volcano. As magma is rapidly evacuated from a shallow magma chamber during an eruption, the roof of the chamber loses support and begins to collapse. This can happen gradually in a series of events or catastrophically all at once. The collapse creates a large depression that can be miles across and thousands of feet deep. Sometimes the collapse triggers even more eruption as it disrupts the magma system. Studying ancient calderas helps scientists understand the processes involved and the scale of past eruptions. Some calderas have been sites of renewed volcanic activity long after their formation, with new volcanic domes or cones growing within the caldera. Resurgent calderas are those where the floor begins to rise again after the initial collapse, pushed up by new magma accumulating beneath the surface. Yellowstone is an example of a resurgent caldera, with parts of the caldera floor rising and falling by several inches over years to decades as magma moves beneath the surface. This resurgence does not necessarily mean an eruption is coming, as calderas can experience uplift and subsidence for thousands of years without erupting. However, monitoring this movement helps scientists understand the magma system and provides information about potential future activity. The cycle of eruption, caldera collapse, and resurgence can repeat multiple times over millions of years, creating complex volcanic systems. Volcanic rocks provide valuable information about the conditions inside the Earth and the processes that created them. By analyzing the minerals and chemical composition of volcanic rocks, geologists can determine the temperature, pressure, and composition of the magma from which they formed. Crystals in volcanic rocks can preserve information about how long magma resided in the crust before erupting and what happened during that time. Isotopes in volcanic rocks help scientists determine the age of eruptions and understand the sources of magma deep in the mantle. This detective work using volcanic rocks has revealed much about how the Earth works and how volcanic systems evolve over time. Columnar joints are striking geometric patterns that form in some volcanic rocks, particularly in thick lava flows and ignimbrites. These are fractures that create hexagonal columns, sometimes remarkably regular and uniform. The columns form as the rock cools and contracts, with the fracture pattern minimizing the energy required to accommodate the shrinkage. Famous examples include the Giant's Causeway in Northern Ireland and Devil's Postpile in California. The columns can be anywhere from a few inches to several feet across, and they can extend through thick rock layers, sometimes revealing themselves as the rock erodes. Ancient peoples often incorporated these natural stone columns into their buildings and structures, and they remain popular tourist attractions today because of their striking geometric beauty. Calderas can sometimes fill with water to create stunning crater lakes. These lakes are often remarkably blue because of their depth and purity. Crater Lake in Oregon is the deepest lake in the United States at 1,949 feet deep, and its intense blue color has made it famous. The lake has no streams flowing in or out, being fed entirely by rain and snowmelt, which contributes to its clarity. Scientists study crater lakes to understand volcanic systems, as changes in the lake water chemistry or temperature can indicate activity beneath the volcano. Some crater lakes are acidic from volcanic gases dissolving in the water, while others are relatively normal chemically. A few crater lakes, like Lake Nyos in Cameroon, have dissolved large amounts of carbon dioxide in their depths, creating a potential hazard if the gas is suddenly released. Volcanic islands and seamounts create important habitats for marine life. The underwater slopes of volcanic islands provide substrate for coral reefs, and the nutrients brought up by ocean currents interacting with the seamounts support productive ecosystems. Many seamounts are the remains of ancient volcanoes that never reached the surface or that have since sunk as the oceanic crust on which they sit cooled and subsided. These underwater mountains affect ocean currents and create upwelling that brings nutrients from the deep ocean to sunlit surface waters, supporting rich communities of fish and other marine life. Commercial fisheries often target areas around seamounts because of the abundant fish populations. Though this has raised conservation concerns about overfishing and damage to seamount ecosystems. The age progression of volcanic islands in chains like Hawaii provides elegant evidence for plate tectonics and hotspots. By dating the rocks from different islands, scientists have shown that the islands get progressively older as you move northwest along the chain, exactly as predicted by the hotspot theory. The Big Island, sitting over the hotspot, has rocks less than 500,000 years old and active volcanoes. Maui, the next island northwest, has rocks about 1.3 million years old and dormant volcanoes. The progression continues with increasingly older and more eroded islands stretching northwest for thousands of miles. This age progression provided some of the strongest evidence for the hotspot theory and helped establish the rates at which tectonic plates move. The island of Iceland is essentially a volcanic wonderland where you can see geological processes that usually happen beneath the ocean occurring on land. Iceland sits astride the Mid-Atlantic Ridge, where the North American and Eurasian tectonic plates are slowly pulling apart. As the plates separate, magma wells up from the mantle to fill the gap, creating new crust and fueling volcanic activity. You can actually walk between the two continents at Thingvellir, a rift valley where the plate boundary is exposed on land. The combination of the spreading ridge and a hotspot beneath Iceland makes it one of the most volcanically productive places on Earth. The landscape is dominated by volcanic features, including lava fields, volcanic mountains, geothermal areas, and the dramatic glaciers that cover some of the volcanoes, creating the potential for explosive interactions between ice and fire. Subglacial volcanoes, which erupt beneath ice sheets or glaciers, create unique hazards and produce distinctive deposits. When magma encounters ice, the ice melts rapidly, producing enormous amounts of water that can lead to catastrophic flooding called jökulhlaups, an Icelandic word meaning glacier burst. During the 1996 eruption of Grímsvötn volcano beneath the Vatnajökull ice cap in Iceland, meltwater accumulated beneath the glacier for weeks before breaking through, releasing a flood that carried huge blocks of ice, some as large as houses, and destroyed bridges and roads. The rapid cooling of lava by ice also creates glassy volcanic rocks and unusual landforms. Flat-topped volcanic mountains, called tuyas, form when volcanoes erupt completely encased in ice, with the eruption melting a chamber in the ice where lava and fragmented material accumulate. The interaction between volcanoes and climate works in both directions. While we often focus on how volcanic eruptions affect climate by injecting ash and gases into the atmosphere, climate changes can also affect volcanic activity. During ice ages, the enormous weight of ice sheets can suppress volcanic activity by increasing pressure on the crust and making it harder for magma to reach the surface. When ice sheets melt, as they did at the end of the last ice age, the removal of this weight can trigger increased volcanic activity. Studies in Iceland have shown that volcanic eruption rates increased significantly as the ice sheets retreated, an effect called post-glacial rebound volcanism. This relationship between ice and volcanic activity is relevant today as glaciers around the world retreat due to climate change, potentially influencing volcanic systems in glaciated regions. Volcanic tremors and earthquakes associated with magma movement provide scientists with some of their most valuable tools for monitoring volcanoes and predicting eruptions. As magma pushes through rock on its way to the surface, it creates distinctive seismic signals. Deep earthquakes beneath a volcano might indicate magma beginning to rise from depth, while shallow earthquakes often indicate magma approaching the surface. The frequency and pattern of earthquakes typically change as an eruption approaches, often increasing in number and moving progressively closer to the surface. Scientists have learned to recognize patterns that often precede eruptions, though every volcano has its own personality and can behave unpredictably. Networks of seismometers around dangerous volcanoes continuously monitor for these signals, providing early warning that can save lives. The crystallization of magma is a complex process that determines what minerals form in volcanic rocks and influences how the magma behaves. As magma cools, different minerals crystallize at different temperatures, with some minerals forming early and others forming later. This process, called fractional crystallization, can change the composition of the remaining liquid magma, making it more silica-rich and more viscous over time. Crystals that form can sink or float in the magma chamber depending on their density, further changing the magma composition. When magma erupts, the mixture of crystals and liquid determines the appearance and properties of the resulting rock. Large, well-formed crystals in volcanic rocks indicate that the magma cooled slowly, giving crystals time to grow, while tiny crystals or glassy texture indicate rapid cooling. Volcanic explosivity is driven primarily by the rapid expansion of gas dissolved in magma. Deep underground, gases like water vapor and carbon dioxide are dissolved in the magma under tremendous pressure, similar to how carbon dioxide is dissolved in a bottle of soda. As magma rises and pressure decreases, these gases begin to come out of solution and form bubbles. If the magma is fluid, bubbles can rise and escape relatively gently. But if the magma is viscous and sticky, bubbles cannot escape easily, and pressure builds up until the magma fragments explosively, shattering into tiny pieces that form ash and pumice. The most explosive eruptions occur when gas-rich, viscous magma reaches the surface, creating eruptions that can send material miles into the atmosphere in minutes. Volcanic ash is fundamentally different from the ash produced by burning wood or other materials. Volcanic ash consists of tiny particles of pulverized rock and volcanic glass, often with sharp, angular edges. The particles are so fine that they can remain suspended in the atmosphere for extended periods and be carried thousands of miles by winds. When volcanic ash falls, it can accumulate in thick layers that bury everything beneath them. The weight of accumulated ash can collapse roofs, particularly if the ash gets wet and becomes heavy. Ash contaminates water supplies, damages machinery, interferes with power transmission, and poses health hazards when inhaled. Cleaning up after major ash falls is a massive undertaking that can take months or years, and ash deposits can be remobilized by wind for years after an eruption. Tephra is the general term for all fragmented material ejected by a volcano, regardless of size. This includes fine ash, lapilli, which are pebble-sized fragments, and volcanic bombs and blocks, which are larger pieces. The distribution of tephra around a volcano provides information about the eruption, with the size of fragments generally decreasing with distance from the vent. However, powerful eruptions can carry even large fragments surprising distances. Studying tephra deposits from ancient eruptions helps scientists reconstruct what happened during eruptions that occurred before written records. Distinctive tephra layers in sediments can also be used to date geological events and correlate deposits from different locations, serving as time markers in the geological record. Ignimbrites are the deposits left by pyroclastic flows, and they tell dramatic stories about some of the most violent eruptions in Earth's history. These deposits consist of a mixture of volcanic ash, pumice, and rock fragments that were hot enough when deposited to weld together into solid rock. Some ignimbrite deposits cover thousands of square miles, and are hundreds of feet thick, representing truly cataclysmic eruptions. The Bishop Tuff in California is an ignimbrite that erupted from the Long Valley caldera about 760,000 years ago, covering much of the western United States with ash. Studying ignimbrites helps scientists understand the dynamics of pyroclastic flows and the scale of ancient supereruptions, information that is crucial for assessing volcanic hazards today. Volcanic domes form when thick, viscous lava is extruded from a vent and piles up around the opening rather than flowing away. These domes can grow slowly over months or years, or more rapidly over days. Because the lava is so viscous, gases cannot easily escape, making volcanic domes inherently unstable and prone to collapse or explosion. When a dome collapses, it can generate pyroclastic flows that race down the volcano slopes. Mount St. Helens has been building a new lava dome inside its crater since shortly after the 1980 eruption, and scientists carefully monitor it for signs of instability. The Soufriere Hills volcano on the island of Montserrat in the Caribbean has been growing and collapsing a lava dome since 1995, with periodic collapses generating pyroclastic flows that have devastated parts of the island. The eruption of the Soufriere Hills volcano transformed the island of Montserrat, once a prosperous tourist destination known as the Emerald Isle of the Caribbean. When the volcano roared to life in 1995, after centuries of dormancy, it produced a growing lava dome that periodically collapsed, sending pyroclastic flows sweeping across the southern part of the island. The capital city of Plymouth was buried under meters of volcanic material and pyroclastic flow deposits, becoming a modern-day Pompeii. Over half the island's population emigrated as 2/3 of the island became uninhabitable. The eruption continues intermittently to this day, and the volcano remains a threat to the remaining population. This ongoing eruption has provided scientists with invaluable opportunities to study dome-forming eruptions and has led to improvements in volcano monitoring and hazard assessment techniques. Volcanic plugs, or lava spines, are another feature of dome-forming eruptions. Sometimes, instead of a dome, extremely viscous lava is squeezed up through the vent like toothpaste from a tube, forming a tall spine of rock. The most famous example occurred during the 1902-1903 eruption of Mount Pelée in Martinique, when a spine grew to over 1,000 feet tall in just a few months before eventually collapsing. More recently, a spine grew from the lava dome at Mount St. Helens in the early 2000s, reaching several hundred feet tall and dubbed the whaleback because of its shape. These features are inherently unstable and eventually break apart or are destroyed by subsequent eruptions. Phreatic eruptions occur when water encounters hot rock or magma, flashing to steam and causing an explosion without any new magma reaching the surface. These steam-driven explosions can happen with little warning and can be deadly despite not involving fresh magma. Crater lakes are particularly prone to phreatic eruptions when magma rises beneath them, heating the water. Geothermal areas near volcanoes can also experience phreatic explosions when the balance between groundwater and heat changes. The 2014 eruption of Mount Ontake in Japan was a phreatic eruption that killed 63 hikers, the deadliest volcanic disaster in Japan since 1902. The tragedy highlighted the difficulty of predicting phreatic eruptions, as they can occur with minimal warning signs that are different from those preceding magmatic eruptions. Phreatomagmatic eruptions represent an even more violent combination, occurring when magma directly interacts with water, whether from the ocean, a lake, groundwater, or ice. The rapid conversion of water to steam creates extremely explosive eruptions that fragment the magma into very fine ash. These eruptions can produce surges of ash and steam that travel at high speeds across the ground, and they often excavate deep craters. The 1883 eruption of Krakatoa became much more violent when the collapsing volcano allowed seawater to flood into the magma chamber, creating enormous phreatomagmatic explosions. Volcanic islands that grow from beneath the sea must pass through a phase of phreatomagmatic activity as they build toward the surface, making the birth of volcanic islands particularly explosive. Mars are broad, low-relief volcanic craters formed by phreatomagmatic explosions. Unlike volcanic cones that build upward, Mars are excavated downward into the bedrock by the violent explosions that occur when magma encounters groundwater. Many Mars fill with water to form circular lakes, and they can be quite beautiful. The Eifel region of Germany has numerous Mars, some of which have been studied intensively because they preserve detailed records of past climate in their sediments. Mars can form in a single explosive event or through a series of explosions, and they represent a significant hazard in areas where rising magma might encounter groundwater. Studying Mars helps scientists understand phreatomagmatic processes and assess hazards in volcanic fields where such eruptions might occur. Volcanic rifts are linear zones of weakness where magma can more easily reach the surface, and they are common features of many volcanoes. In Hawaii, rift zones extending from the summits of shield volcanoes can be sites of spectacular eruptions. The 2018 Lower East Rift Zone eruption of Kilauea produced lava flows that destroyed hundreds of homes and dramatically reshaped the landscape. Fissure eruptions along these rifts can produce curtains of fire, where lava fountains along a crack in the ground, creating a spectacular display. The lava from rift eruptions often flows easily and can travel long distances, making even relatively gentle eruptions hazardous to anything in the path of the lava. Understanding rift zones is crucial for hazard assessment at volcanoes where they occur. The formation of new volcanic vents during eruptions can dramatically change the hazard picture. Sometimes eruptions open new vents far from a volcano's main crater, potentially threatening areas previously considered safe. The 1943 birth of Paracutin volcano in Mexico occurred when a new vent opened in a cornfield, producing a cinder cone that grew rapidly. More recently, the 2018 Kilauea eruption saw new fissures opening in residential neighborhoods, destroying homes and forcing evacuations. Scientists monitor volcanoes for signs that might indicate where new vents could open, including patterns of earthquakes and ground deformation. But predicting exactly where new vents will appear remains challenging. This unpredictability is one reason why large exclusion zones are often established around active volcanoes. Volcanic seismicity includes not just earthquakes from rock breaking, as magma pushes through, but also distinctive signals from magma and gas movement. Long-period earthquakes have lower frequency vibrations and are thought to result from fluids moving through cracks and conduits. Very long-period events last even longer and may reflect larger-scale processes like gas slug movements or resonance of magma chambers. Volcanic tremor consists of continuous vibrations that can last for hours or days. Each type of seismic signal provides different information about what is happening inside the volcano, and scientists have learned to interpret these signals to understand volcanic processes and forecast eruptions. The development of machine learning and artificial intelligence is now helping scientists better recognize patterns in volcanic seismic data. Ground deformation monitoring has become one of the most reliable methods for detecting magma movement beneath volcanoes. GPS stations measure horizontal and vertical ground movement with great precision, detecting the swelling that occurs as magma accumulates or intrudes beneath a volcano. INSAR, which stands for Interferometric Synthetic Aperture Radar, uses satellites to measure ground deformation over large areas by comparing radar images taken at different times. This technique can detect changes of just a few centimeters across entire volcanic regions. Tilt meters directly measure changes in the slope of the ground, which can indicate inflation or deflation of a volcano. By combining data from these different instruments, scientists can create models of how magma is moving beneath the surface, providing crucial information for eruption forecasting. The gas emissions from volcanoes provide a direct window into what is happening at depth, as gases released at the surface have recently come from degassing magma. Measuring the ratios of different gases, particularly carbon dioxide to sulfur dioxide, helps scientists determine whether magma is deep or shallow. Increases in gas emissions, especially of sulfur dioxide, often indicate that fresh magma is rising toward the surface. Scientists use various methods to measure volcanic gases, including ground-based spectrometers, drones carrying gas sensors, and satellites that can detect sulfur dioxide plumes from space. Sometimes scientists must work in dangerous conditions, approaching active vents collect gas samples or install monitoring equipment. The data they collect is invaluable for understanding volcanic systems and providing warnings of potential eruptions. Thermal monitoring uses infrared sensors to detect heat from volcanoes, which can indicate changes in activity. Satellites equipped with thermal sensors can detect hot spots from space, identifying new lava flows, growing lava domes, or increased heat from crater areas. Ground-based thermal cameras can provide detailed views of temperature changes at active craters or lava flows. Increases in thermal output often precede or accompany eruptions as hot magma approaches the surface. During eruptions, thermal monitoring helps track lava flows and assess their advance rate, providing crucial information for emergency managers and communities at risk. The MODVOLC system automatically processes satellite thermal data and provides near real-time information about thermal activity at volcanoes worldwide. Volcano observatories around the world work continuously to monitor active volcanoes and provide warnings when eruptions threaten. These observatories collect data from vast networks of monitoring instruments, analyze the data to understand what volcanoes are doing, and communicate hazard information to government officials and the public. Some observatories, like the Alaska Volcano Observatory, monitor dozens of volcanoes spread over a huge area, many of them in remote locations, accessible only by helicopter. Others, like the Montserrat Volcano Observatory, focus intensely on a single dangerous volcano. Scientists at these observatories often work in challenging and sometimes dangerous conditions, maintaining instruments in harsh environments and sometimes working near active eruptions. Their dedication and expertise help protect millions of people living near volcanoes around the world. Volcanic alert levels are standardized systems used to communicate volcanic activity and hazards to officials and the public. Different countries use different systems, but most have several levels ranging from normal background activity to major eruption in progress. In the United States, the USGS uses a color-coded aviation alert system alongside a volcanic alert level system. Changes in alert level are based on monitoring data and the judgment of scientists about the likelihood and potential impact of volcanic activity. Raising the alert level triggers actions by emergency management agencies and can lead to evacuations or other protective measures. Communicating volcanic hazards effectively is challenging because volcanic unrest can last for months or years without resulting in an eruption, potentially leading to complacency or alert fatigue in communities at risk. Evacuation decisions during volcanic crises involve balancing the risk of eruption against the costs and disruption of evacuation. Evacuating too early or too often, when eruptions do not materialize, can lead to economic losses and erosion of trust in scientists and authorities. Evacuating too late or not at all can lead to deaths. Scientists can provide information about the probability and potential magnitude of eruptions, but officials must make decisions about evacuations considering social, economic, and political factors. Successful evacuations require advanced planning, including identifying which areas are most at risk, establishing evacuation routes and shelters, and educating the population about volcanic hazards. Communities that have well-developed volcanic emergency plans and conduct regular drills are much better prepared to respond when a crisis occurs.